everyone, this is Mustafa. In this video I am going to talk about recipes. Due to necessity I have introduced this topic briefly, but in this lecture we will be checking contents of recipe examples and explain the sort of syntax and variables used in the recipe files. In order to cook a recipe file, we learned that we need to run bitbake command on it. For example, we can now let us cook the actual nano recipe, nano software package. So we're going to just say bitbake nano. Okay, apparently it was already cooked, so if you would like to clean the simply recipe output, what you can do is you can type in bitbake nano c and you can say clean all. This will basically remove all the build outputs in the work dir, in the build tmp work directory, so that you can start fresh. This sometimes might be needed in order to overcome some issues. But let's not do this for the moment. We have already our bitbake nano. So as you recall, we said that each recipe has some tasks to execute in order to come up with the build outputs from source. So let's first examine what these tasks are for nano software package. I expect for most of the regular software package recipes, the tasks are going to be similar. However, there could be additional tasks added to some software packages based on the nature of them. And these tasks are mostly all described within the meta layer that already comes with the Open Embedded. So we are learning these in case in the future we would like to customize a specific task. So let's simply go inside the work dir for the nano software package. It should be somewhere here, I believe. Yes, it is. And as you recall, we check the task order by simply going inside the temp, and then we have used this task order file. Alright, so as I said, these tasks are mostly similar in many software packages. If you are adding support for some different build system, for example, then you will have to define some of these tasks by your own. As an example, Qt comes with this QMake build system support, and some of the layers are overridden in their bbuild class file. So if you want to use QMake in your recipe, for example, you will be simply inheriting the class that defines these tasks. Okay, so let us now start describing what all of these tasks do in case for the nano software package. First task is do recipe QA, which is recipe quality assurance. In this task, simply bitbake ensures that the recipe is correct. There are some variables that needs to be defined for a recipe to function, such as the source code location. Source code location we give with this variable called actually. I can show you directly. So it is crc_URI. And basically this task checks the content of variables such as this one, and if there is any problem, if the source haven't been specified, then bitbake will simply throw an error. This is the case for the do recipe QA. Then comes the fetch task. In this task, the source link or the source URI we just described with this variable will be simply downloaded under the work directory that is simply related to this software package. If there is any connection failure, bitbake will be throwing an error here. Then comes the unpack task. In this task, if what was downloaded is an archive like a tarball or a zip file, it will be extracted to the folder dedicated to the recipe work dir, which is under build tmp work as we saw. So we will be pointing to this location by using the work dir variable with this one. Okay, essentially this unpack task extracts the archive to work directory, which is accessible with the work dir variable. Next task is this do prepare recipe sysroot. This task simply prepares the sysroot. And what was sysroot? In this task, the dependencies of the software package simply will be copied from their respective dedicated work directories into a folder called recipe sysroot. And we have already seen this. Let's check it again. Here it is. So all the dependencies are collected from other work dirs into this one, the output. And then the compilation will take place by using this sysroot. So there is sort of a level of isolation between the environments when Bitbake is simply compiling or cooking a recipe, because the environment for this case, for this nano case, is inside here, all the libraries, all the dependencies. And for the tools, for the host tools, it will be located under here, recipe sysroot native. All right. Then comes a task that collects the SDPX output dependencies. This SPDX, we won't go into detail, we don't care about it, but it is simply some standard for describing software packages that includes components of the software, some definitions, some licenses, and so on, but we don't care about this. This is essentially related to some package management. Next up, we have do-patch. With this task, the patch files you have added to the source URI will be basically patched on top of the software using the default patching tool. So in this variable, we will be adding patches if we have any. Then during the patch task, then these patches will be identified and automatically patched on top of the original source, provided that you give the correct folder layout, correct location. So in Yocto, basically there is option to specify this patching tool, but the default one, as far as I know, for Yocto is Quilt. So it is basically a patching tool called Quilt. Then we have another task. We don't need to cover this. Then comes the populate licenses. We have to use another variable which is called license, and in this license variable, and also we use another variable called license files checksum. Both of these variables are used during this population of the licenses. We basically give the license type and the license location, and basically what happens is these two variables are parsed and the licenses are populated in the respective work directory of our software package. The license is mostly important for software packaging step. So if we are starting as a beginner, then you can simply give a closed license. So if you type here closed, then no license will be checked and you will be good to go. So for starters, I would recommend this. If you don't give anything here, then the Bitbake will throw an error complaining that there is no license. But if you are caring about the licenses, of course you will have to do it properly. You'll have to give the proper license, and then correct license type and the correct license name. Then we have the configuration task with the name doConfigure. With this task, simply goal is to execute the configure script if it's present in any build system that the source code uses. For example, the original software package can use GNU Auto Tools, and the configure script that will be executable with the name configure, and it will be executed within this task. To be able to specify the configuration options, we will also be simply setting some variables for this task to simply function properly. Then comes our compilation task. In this task, simply expect some make commands inside or some simple compilation with the GCC command line. We can, of course, on top of what's defined in the make file, we can add flags to the compilation from the recipe file. So from outside the original make file, we can simply add some options to our compiler by defining some variables such as C flags or CXX flags. It will be also possible. Alright, we have our install task. After the compilation, the purpose of the install task is to simply run make install on the available make file, and this will make the outputs from the compilation to be deployed to the folder dedicated for creating the root file system. We have the package related tasks afterwards to create the package folder containing the data for the package and the package itself. So these two tasks, I don't want to go into so much detail here. And we have a task for creating the SPDX output, which, as I explained, is some output containing the software package related information, though we won't use it, some quality assurance for the package, and then comes a task generating the RPM file based on what was collected in these tasks. So this is the one actually generating the RPM output, and then we have again final task to create some runtime for the SPDX standard, not important for us, and then final one is to populate the sysroot. This population of the sysroot basically involves populating everything to the sysroot and making sure that, for example, the binaries are stripped of the debugging symbols and so on. Alright. Here, as you can imagine, we can list most of the important tasks as fetch, unpack, patch, configure, compile, install, and package. These are the essential tasks. For some software packages, we will see that some of the tasks are actually simply doing nothing, because for some software packages, some tasks are not going to be needed. For example, if we don't have anything to unpack, if we don't have any archive, then unpack task simply can be empty. It won't need to be executed. Let us move to an example recipe body in order to explain how recipes are constructed. For example, this file that you can see, this file content is very basic recipe file for simply cooking a software package that has only one C file. There is no make file. We just need to compile the C file and install it to the proper destination. So for that, we can write some recipe such as this one, and let's start explaining it. So first up, we have some variables, let's say, describing simply the package itself. So we can have a variable with the name description. We can have a variable with the name summary also. We will be describing it, and in the software package, this will be recorded in the software package output. Then we have the section to select some category for our package. Okay, it's optional. You can give it or you can choose not to give it. Then we have explained we have to specify some license for our software package. This can be closed, as I told you. If it's not closed, then you have to give some other file. And simply we are pointing to the copyright that is simply located in our work directory. And in this example, our source URI, which is the folder that's containing our source, is basically also same as our work directory. We gave some MD5 in order to provide the checksum for this copyright file. Then we come to the PR. Basically, PR is also optional. This is simply stating the package revision. There are 3 variables that you can use in order to specify package name and package version. Those could be something like this. So package name is denoted by PN, and you can override the package name here. For example, Hello World C. You can use another variable which is PV in order to give a version. Let's say that our package version is 1.1.0.0. We can also specify this, and what we can also do is we can simply give a revision for our package. So we have the option to define these, but we don't need to do them because these variables are simply extracted from the file name if you don't give them. Alright, so for example, let's disregard the package revision for now. Let's say that our package name, we want it to be Hello World C. We want the version to be 1.0.0. So we can either set this up in the recipe body, or we can simply not do that and just name the file. And file name will be Hello World C underscore package version.bb. So if we do this naming, then this will be simply assigned to the package name, and this will be assigned to the package version. That is something important to keep in mind. And since these are automatically assigned to the PN and PV variables inside, you can use these variables. So for example, if I'm doing anything in this file, I can now use PN variable in order to simply refer to my package name. So I can do this. In this case, this name will be copied here. So Hello World file recipe, it will become. Alright. Then comes the source URI. Source URI is very important. Source URI is a variable that is used in order to include any file in the work directory. You can specify a list of containing folders, C files, archives, patch files, kernel config files here. Depending on task you are on, these files will be interpreted differently. However, the main purpose is to simply copy files to work directory so that you can start doing operation of those files. here we are not only limited to local files or folders, we can also give here Git repositories and tarball archives. If you give a Git repository here, then during the fetching task, the repo will be cloned to the work directory under a folder called Git. If you give a tarball archive here, then during the fetching task, it will be extracted to the work directory under a folder with tarball's name. For example, if you give a patch file here, then the patch file will be used during the patching task in order to modify the source files. So we have a lot of flexibility here with this variable, and in the start it can be confusing, but what I want you to recall is simply that this variable is used so that we can include whatever we will use during build in the work directory. So what happens is these files will be available in the work directory if we haven't specified any separate work directory. Alright, for example, you have a local file, right? You want to give, I want to give some txt file from opt, for example, a.txt from my development PC. I can also do it. So this location is path in your development PC. But once you do it, and after this do fetch task, then this will be copied inside some source folder. Alright, so for example, for this nano, where is the source? It's this folder actually. So when we type in s variable anywhere in nano recipe, we will be simply referring to the path to here, nano-7.4. As you can see, it is our source. We don't have any bb class. We are not referring to any other file here. So we are just using what is available in the bitbake directly. Actually, let me get rid of this so you can see better. Alright. Here we have the compile task, and here we have the install task defined, because these were the only ones that are needed to be customized. The other ones, we don't need to customize anything. Most of the packaging stuff will be automatically handled by OpenEmbedded. And also the unpack task, for example, automatically handled. So what we need to overwrite are those two. First, we are specifying how to compile this, and second, we are specifying how to install this to the destination folder, to the folder that we will use in order to create the image if this software package is involved in the image. Okay, so let's check compile task. It is simply bash, right? It's nothing special. You just use some variables in order to refer to the paths using this OpenEmbedded environment. But other than that, it's simply shell. So we are referring to the C compiler. CC variable will be pointing to the GCC that the bitbake is already using. So it will be cross-compiled. Don't worry about it. And we just use CC. Okay, we just give the location of the source by workdir slash something that we already gave here, but I have removed it, so let me correct. And then we give the output name. Let's say that the output will be hello YP, whatever. And we have also gave the where this binary will be generated, right? Where this binary will be outputted, so it will be under workdir. And so in the install stage, we can give first where this should be installed. Basically, this install-d is similar to making a directory. So if this directory doesn't exist, it will create it. I'll explain what this directory means. And then we have this install command, and here it is basically copying. Set the permission to 755 and then copy this file to this location we are telling. Alright. So let's check where this workdir is. What this workdir actually refers to is directly this one. Directly before going into any of these build or image or source directory, we have our workdir just one level below. So this one is it for the nano software package. We have, of course, haven't cooked this recipe yet, but we will do it also. And this D is simply what's inside this image. So if I am deploying something, if I'm copying something from work directory to the destination, it will be copying to the image folder basically. But I do need to do this because this will be used in the image generation. My outputs should go to the destination directly, and I specify this with the D. And then there's this binder variable. Binder variable simply is USR bin. So nothing special actually. This is the fancy way to do it. So what will happen, this image USR bin directory will be created if it's not created, and then from my work there, one level below, there will be the output hello YP here, and then it will be copied to the image folder. Alright, as you can see in Yocto recipe, we work a lot with these variables. I also want to talk about something else, which is creating a task with Python. The only difference is you give this Python in the name before the task name. So if I'm defining some task, for example, I will say do some task, and I will say Python, and then I can do whatever I can in this function block using Python. Of course, BitBake comes with libraries that you can use in order to achieve basic tasks. Also important to know those, but maybe we will take care of them a little bit later. Maybe we won't. I haven't decided yet. So now we can create our first recipe. Let's get rid of this line, and then we will be creating our first recipe. Alright, so we have our own layer. We will be, of course, creating the C file also. We don't have a C file yet, but let's say that we want something under recipes dev tools. Let's say that our C file is responsible for creating a developer tool. Okay, inside we will create a folder that will be containing our package name. It was hello world C. Okay, and inside we will create our file with the package name underscore version dot db. This structure of the file name you can see a lot in the other layers as well. And sometimes the version is actually git here, right? So if you specify something like this, the version will be automatically assigned by using some of the git revisions. So it will not be some fixed version that you're referring to. It will be some revision in some git repository. But for example, for this software package, we immediately we can tell that the package name is BCM2835 and the package version is 173. Okay, so let's copy what we have explained. We have our summary here section. I don't want to give, and I don't want to deal with the license for now. And then I don't have a copyright. I have only one source URI. If I inherited something, maybe I could have used this append, because maybe the BB class would use this originally, but since I don't have it, I don't need to append to it. I just override it or define it, and this will be hello yp.c that I will create, and in the do compile, simply compile it from the work directory, and the output will be this binary, and then install will be all intact. One thing to keep in mind here, for example, in this case, our source file will be deployed to the work directory, right? Since our source file will be deployed to the work directory, by default, our source will be work directory itself. So we can avoid that by simply overriding this s variable, and we can say, for example, work dir my source, and yeah, we can simply override this one, and our source directory will be this one. So whatever it is here will be actually inside the my source instead. Now actually let's go with that. This is a better approach. So now then, since our source is here, we won't be directly using this source work dir. We will be using this s variable pointing to the source location, and you can say here b for the builds, and let's see what comes up actually. Alright, let's check if this works, and we will debug it together so I don't always remember everything. We will see, but first also we need to create our C file. Let's create our C file, just here because we this path simply file location starts from this recipe path, so we should be creating it here, C file here, if we want to give the source URI with this statement. But we can also create one directory and simply give the directory as an extension to this source URI search location. We will do that later. Okay, so let's say hello yp.c, and inside include some stdio hash, and int main void, let's say printf, it works, let's return 0, and let's compile that. Okay, I think it is looking good, so we're ready to build our first actual recipe that we written. Okay, for first sourcing it, and bitbake hello world C. This was the package name, hello world C. Alright, so we have one error, which is unparsed line, and I can see immediately what the issue is, because we have this unorthodox character here. So since I have copied it from the presentation, this character is not a double quote actually, so let's go ahead and copy this and paste it here and give it another go. Alright, we have another here. So this tells me some important stuff actually. I was wrong to put this here. It says that I'm already searching for this files directory, right? So in this case, I need to put this under some files folder. So I cut this, I paste it here. Alright, let's give it another go. Okay, nothing provides hello world C. Good to know. My mistake is obvious here. I should have moved this source file to here instead of the recipe. So I will simply cut this and put it here. So files will contain the source basically, and simply this recipe will be inside this hello world C directory. Okay, you can see it has been started, but I have an error. So in the error case, first thing you would like to check is simply this where the error occurred. It is apparently this do compile where it has occurred. So I have something wrong with my do compile step. Let me check it quickly. So it gives some fatal error saying that no such file or directory. So I can debug this. What I can do is I can check where this C file is by going inside my TMP work and then going inside one of these folders and C, and I can see that the source file is in the work there. It's not inside the my source at the moment. Obviously there's some mistake that I did. Alright, to be able to put this also inside the source, I think what I'm gonna have to do is create here a folder with my source and put this one inside like so, and then here in the source URI give this my source, and let's check this one. Okay, now it is complete. So this tells me what? This tells me that simply in the source URI you should keep the same structure that you would want it to be in the work directory. Alright, I have another issue. Let me check. This is regarding the package QA. So this is some quality assurance related thing. My compilation has been already successful. For issues like this, you can simply search online. So I will do the same. I remember this, I learned this, but I don't know, I don't memorize how to fix it. So let's do it together. I'll simply search it. Didn't pass LD flags, and it is telling me to add this simply, or add a skip of this check. So you can use this statement to check some quality, simply avoid some quality assurance steps, or you can use this. I want to do this one first, just in case. This is simply passing the LD flags to the target to avoid this QA issue. Let's give it another go and see if it is successful. Okay, as you can see, it was successful. So let us quickly check the outputs. Build TMP work, our compatibility machine, and then we are going to go inside Hello World C, and then let's first go inside the my source. Here the build directory and the source directory is apparently the same directory. So we have our output here and the C file here. What else we can check? We can check the image. As you can see, we have the binary deployed to the USR bin, and that will be useful in image generation. And we have also Hello YPC here. This is a residue, I believe. So this is from our previous build. So if I simply clean it and rerun it again, I don't expect the C file. Let's check if it works. Let's do hello world C clean all, and then first clean all, then simply cook the recipe again. Hello everyone, so this is Mustafa. In this lecture, we will explore Raspberry Pi configuration, and then we will see how to create our first Raspberry Pi image. As you recall, our PSP layer that we downloaded is called Meta Raspberry Pi. This layer comes with support for Raspberry Pi 5 machine. We have already added this Raspberry Pi 5 machine to our local conf file, so that the build system is aware of the fact that we are building for Raspberry Pi. In order to create our first image, we need to take care of a few things. One is to make sure that we set up source console parameter correctly, so that we can see the boot and the console output from the correct UART port. Second thing we need to take care of is, since we are in the debugging stage, it would be good to add an SSH server to our image, so that we can also use SSH communication in order to connect to our board. In this lecture we will be exploring these options, but first let's talk about introduction to the Raspberry Pi 5 hardware. I will not go so much into detail, as I expect the listener to be familiar with the Raspberry Pi already, but to put simply, this is a single board computer that is very popular. There is a big community around it, most of the things, besides a few firmware is open source. That is actually why we are using Raspberry Pi 5 for this lecture. Checking the specs, you have enough power for many applications. If you would like to implement some deep learning or hands-on application, you can look somewhere else. in my
or
build
if you're
now, in
looking
my
to develop
image,
some
I
time
should
critical
do
application, you can
build
look somewhere else.
conf
But other than those
locals,
GPU intensive or safety
add it
critical
here
applications, I
directly.
think Raspberry Pi 5 is more than capable of handling many tasks. It has sufficient RAM, a good ARM Cortex A76 based SoC. SoC is
And
called
then what I can do is I can
BCM2712, and it also comes with a lot of peripherals and
another
connectivity
build,
support. It has two mini HDMI's,
and
gigabit Ethernet,
corresponding
USB
big image
3.0
or
ports,
SD card image will
Bluetooth,
contain this
Wi-Fi,
root
and
file.
this recent Raspberry Pi 5 comes
Alright.
with a PCIe
So thank
interface
you very
also,
much
which
for
is
your
really,
attention,
really good.
and I will see you
One
in
thing
the
that's
next
important, Raspberry Pi comes with one peripheral or I/O controller chip